Welcome back. Today we're going to see an example of group action that you don't expect. Did you ever think that the solutions of a differential equation could give me an example of Lie group action? That's one thing we're going to check out. More than that, we're going to see if we have a collection of differential equations with some compatibility condition among the differential equations. We will check that there exists the group action. A group action. Which group? Stay tuned. It's going to be a very short video. I hope you like it. I'm going to check that. So the question is, do differential equations give us examples of Lie group actions? And the answer is yes, much more than you expect. Of course, the whole motivation of Lie to start looking at Lie groups comes from solutions of differential equations. But what I want to show you is very simple. Because I want to do a short video today, what I'm going to do is to make some assumptions, some reasonable assumptions. So the first assumption I'm going to make, it's a stronger version of the assumption, is that M, it means M is the manifold where this differential equation is defined. So the differential equation I'm considering is of this sort. But now this X runs on a manifold, right? So I assume that X is a vector field on a smooth manifold, which I call M. Okay? So a strong assumption would be to assume that M is compact. I agree with you. If you think about your favorite differential equation, or you think about a mechanical system that has a differential equation associated to it, then, well, the ambient manifold you consider, the phase space, whatever, is non-compact. But believe me, it's worthwhile to think for a while, simplify that M is compact. If M is compact, one thing we know is that the flow of this vector field, so I'm going to consider flow of the solutions of the differential equation, let me call this the flow of the vector field X. This means that when I evaluate the vector field along the image of the flow at points on the manifold, this is the same as the differential of phi t, okay, over t. That's the equation we are indeed considering, okay? That's what we call the flow. An interesting thing happens when M is compact. So one interesting thing we know is that M compact implies that phi t is defined for all t in R. Okay, now consider G to be R, okay, with the additive. So I consider the additive group of real numbers, okay? Then one interesting property, one relevant property that we know of flows that I'm not going to prove, I'm going to assume that you know this, is that when I compose, if I advance in time, this is the same as composing. That's one of the properties that we have, composing of the diffeomorphism of the flow. Well, that's a property that we have to know from differential equations. Okay, now let me change the language for a while. In a different language, consider now as group the real numbers. Okay, consider as manifold the manifold where this flow is defined, and now consider the following action. Take a point on the real line and take a point x on the manifold and send this to phi sub t of x. This is a diffeomorphism acting on x, so this is a perfect point defined on M, and what you can check is that the condition, this property of the flow, can be translated as saying that alpha defines an R action. So there you have an example of our action just considering the solutions of a differential equation on a compact manifold. Can the compactness condition be relaxed? Well, the only thing I need to guarantee is that X has a flow defined for all t, and this has a name, okay? This has a name, so we may replace, remark, we may replace compactness of M by completeness of X, of your vector field. This means a vector field is complete if its flow is defined for all t. And then you have exactly that this is an action of the whole R. Otherwise, we wouldn't be able to put here an R. Okay, a generalization of this idea, quick generalization of this idea. Consider now K vector fields. X1, xk on a manifold of dimension n. Okay? And look at their defined differential equations, which I may consider to solve not as a system of differential equations, but as a system of independent variable equations. Okay, so I may consider indeed the system of equations. I'm going to denote by phi1 the flow of x1. Okay, and I consider this. So I'm going to change the notation maybe. Let me erase this. Let me consider as notation. Let me put super 1 sub t. Okay, that's the flow of the vector field x1. And now I could do this for all the vector fields, including the last one. So phi k t, d phi t, and here super 1, and here super k t. Let me call this like t1, t1, and this tk, tk, right? So in general, we are considering vector field of this vector field, let's call it I, phi I ti. Okay, let me put here equals d phi I ti differential of ti. Okay, that's the condition I'm considering. It would be interesting to see if we can solve this system of differential equations for these different parameters. And well, the ones who have been dealing with foliation theory know that if the vector fields commute, we have an interesting thing going on for all ig from 1 to k. If all of them commute pairwise, then an interesting thing happens. Their flow are also going to commute. That's a property that I'm going to assume. Then their flows, super I, Ti, composed with phi super j Tj, is going to equal phi Tj super j composed with phi Ti super I. That's something I'm going to assume, okay? Again, I'm going to do like I did before here, and I'm going to translate now this, I had translated this condition as a condition of the flow, as a condition of our action. And now the interesting thing, and this is what I leave as an exercise that I want you to think about and let me know if you understand or not. So the exercise I want to leave now check that if we assume either M compact or all the vector fields x sub I complete, of course, and we assume, if we assume either this or this and the commutation property, then I want you to check that the mapping okay, now here I have, let me correct this. This is on, it's an RK, okay? Where K is the number of vector fields we have that commute, okay? And now I send this to the composition super K, okay, point X, that I compose with phi Tk minus 1, K minus 1, and I compose here with phi T1 super 1. So you can check that this defines an RK action where the action here we consider the additive group structure. Okay, I leave this as an exercise. This is an interesting checkout because you need to check the definition, check the condition. So, well, let me erase here, change color. So what I want to say is the hint, the only hint I need to give you is that, okay, I need to check that the sum of vectors here goes to the composition, right? Because need check that the sum, so my hint is just the definition, check that the sum goes to the composition. But then when you have to check that the sum goes to the composition, then apply this property here of exchanging. So, well, my hint is just apply the condition of commutation of flows. Okay, that's the hint I want to give. Now, interesting applications of this thing. Let's talk about applications. So one may think, like, when do you have these things in real life? One may think, oh, well, can you assume that you have these vector fields and commute? So applications or examples where these situations crop up, I want just to hint a couple of them. The first one is the case of integrable systems on a symplectic manifold that will show up really soon. That's the next topic we need to deal with, symplectic manifolds. Okay, and here we have a natural way to associate these vector fields. Indeed, we associate these vector fields, these commuted vector fields, to functions, and we have a way to do this which is determined by the Hamiltonian systems. Okay, Hamiltonian systems are a way to convert vector fields onto functions and functions into vector fields, because we associate to a certain system the energy, and the energy is just a function. Okay, then when we consider an integrable system, it means that I take n functions. The definition is super simple, and I assume that they Poisson commute. This definition of Poisson commuting, it's simple. When you have the symplectic form, you can write it like this, when these guys are the Hamiltonian vector fields. So I'm going a little bit too far away, because this is a little bit away in what we plan to do. Okay, this comes later on. So this is something that we are going to say. This is an attention spoiler. Attention spoiler. That's on a spoiler of what comes next. What comes next is that here I just consider some functions, and to these functions, thanks to having the definition of integrable system, we associate to these functions a collection of vector fields, and the condition of the bracket, the Poisson bracket being equal to 0, translates into the condition that the Hamiltonian vector fields associated to this function commutes. So that's a natural example, and in this example, K is equal to M, and the dimension of the manifold is 2n. Another example, example 2, is that of affine manifolds, which are so well known, you know, in Riemannian geometry. An affine manifold is a manifold whose change of coordinates is affine transformation. And the interesting thing is that in the case of affine manifolds, you do have, if you have a manifold of dimension n, then in this case, K is equal to n. Okay? And you have indeed K vector fields, n vector fields that pairwise come. So that's two very different applications, one from Hamiltonian dynamics and one from Riemannian geometry, or you may think of other you know, differential geometry in general. And you may think of applying this a nice result of group actions. You'll see why this is useful, essentially related to the case in which when we have periodic orbits, sometimes we are able to normalize the periods. If we have periodic orbits for each, if each of the orbits is periodic, sometimes we can normalize the periods, and this is what is going to later give us the notion of Arnold-Liouville theorem. That's in the case of integrable systems, not so far from affine manifolds, and we will be able to prove Arnold-Liouville theorem. thanks to this kind of normalization of periods. Okay, and this theorem is fantastic. It's going to tell us that if you have an integrable system such that the fiber is compact, first this fiber is a tori, and then you have a fibration by tori. That's fantastic. And we're going to be able to prove this using a group action. I said this was going to be a short video, and I stand to where I was. Let me finish here the video here, and send me emails if you have questions. See you next time.